Hi, my name is Zhead from the Ohio State University. I'm presenting Revisiting Model Stitching in the Foundation Model Era, collaborated with Boston University and Amazon. The key question we try to explore is, can heterogeneous vision foundation models, or VFM, be connected, felt, and served more efficiently? We try to answer these questions from the lens of model stitching. We found that with appropriate stitching, different VFMs are not just compatible, they can be complementary. Moreover, we show that stitching can move from being just a representation analysis tool to become a practical recipe for fusing complementary VFMs and reduce the cost in multi-VFM systems. Nowadays, VFMs are often trained with totally different data, supervision signals, and training objectives. In our another CVPR 26 paper, Ava Bench, we show that they have some common strengths, but also demonstrate very unique specialties. So with this, we may ask, are VFM fundamentally different end-to-end, or are their internal representations similar or compatible in some layers? Additionally, to leverage the specialties of different VFMs, a common practice is to run several VFMs in the same systems, but they scale memory and latency linearly. So with the better understanding of the internal representations, can we serve multiple VFMs more efficiently? We try to answer this question through model stitchings. So we can connect the shallow layers of a models to the deeper layer of another model with a stitch layers to form a stitch models. And in the stitch models, only the stitch layer is trainable, and all other layers in both models are frozen. So if the stitch model has minimum performance drop, it means their internal representations are similar. However, how to train the stitch layer is not trivial. We found that naive stitching fails in the VFM regime. For example, layer feature matching, which aim to match the features at the stitch point, does not work well for VFM. And the main problem is that a small difference at the stitch positions could accumulate and be amplified by the frozen target layers, and you can see a much bigger final feature differences. For example, if you stitch at layer 2, you can get very small feature differences at that layer because that's what the training objectives optimize, but you will see a much larger final feature differences. So to handle this, we'll propose to use final feature matching, which tries to match the final features between the stitch model and the target models. So as you can see here, when using final feature matching, you can get a much smaller final features differences even when you stitch at early layer. And because of that, we also observed that final feature matching can get better accuracy than layer feature matching. So to get better downstream performance, another common stitch method is task loss training, which optimizes the downstream loss directly. But it also has several problems. So when you stitch at very shallow positions, all the post-stitched target layers are frozen. So the gradient at the prediction head must backprop through a very long and fixed transformation to update only the stitch layer. And this can lead to some optimization challenges, especially if the stitch layer is randomly initialized. So as you can see, training the stitch layer directly with the task loss can get much worse performance than the original VFMs and other stitch methods. So this is our simple but effective two-stage stitching recipe. So in the first stage, we do the label-free final feature matching, which tries to match the stitch models and target models' final features. And this also places the stitch models in a better loss landscape. With that, in the second stage, we will adapt the stitch model to the downstream task. So as shown in these figures, the stitch model shows much better performance than the original VFMs. So to fully understand where do the accuracy improvement come from, we study the self-stitch baseline. So in this baseline, we insert the same stitch layer into the source-only and target-only models at the exactly same stitch position using the same training data and objectives. So this can isolate whether the accuracy improvement is only from the stitch layer. And this is a demonstration of the self-stitch. So as we can see here, the stitch model consistently outperforms the self-stitch baseline. It means stitching heterogeneous VFM is not only feasible, but also has the potential to force the complementarity between them. So, the stitchability is not just a one-off cherry-pick result, but it's a general observations. We verify this across different tasks, datasets, models, pre-training data, and stitch layer families. Motivated by the stitchability of VFMs, we propose the VFM Stitch Tree (VST), which share common shadow layers across VFMs while retaining model-specific dip layers, and all this connected via stitch layers. VST serves as a simple and efficient alternative to naively running all the VFM end-to-end, which wastes a lot of GPU memory and computations. This is an example of VST in a lava with two VFMs. So VST can achieve much of the two VFM gain while with way lower overheads. To summarize our paper, we found that stitch layer training matters for VFM, and with our proposed training recipe, stitching can fuse the strengths from different VFMs. And the proposed VFM stitch tree can turn multi-VFM models into a controllable accuracy and latency trade-off. So our work aimed to turn the model stitching from a pure representation analysis tool to a practical paradigm for integrating heterogeneous VFMs. Thank you.